Katrina here, and today I'm going to show you how to derive Bayes' theorem. So Bayes' theorem is very important in probability and statistics. So make sure you watch to the end of the video so you can see how this is derived, and please subscribe for more of my videos. The first thing we're going to look at is a joint probability distribution. So let's consider some p of x, y. So this is a joint distribution. So this means that we're looking at what is the probability that event x and y occur. So with this joint distribution, we have to understand a few other aspects. So if we were to just consider p of x or p of y, these are called marginal distributions. So that's when you're just looking at one part of it. So there's a rule called product rule, which relates joint distributions to the conditional distribution and the marginal distribution. So we covered marginal, but what's a conditional distribution? So say we have some p of x and this bar and then y. So this is considered a conditional distribution. So that means that the values of x depend on y. So what is the probability of x occurring given that y has already occurred and we know the outcome of y? So like I said, we can now relate these two ideas together, conditional and marginal distributions together, through this concept known as the product rule. So the product rule states that if we have some joint distribution, p of xy, so that's the probability of x and y occurring, this equals to the sum of the conditional probability of y given x multiplied by the marginal probability of x occurring. So the product rule can be interpreted as the fact that every joint distribution of two random variables can be factorized and written as a product of two other distributions. The two factors, like I showed here, are the marginal distribution of the first random variable, p of x, and the conditional distribution of y given that x has occurred. And what's really important here is that ordering does not matter. So what does that mean if ordering does not matter? Well, that means that we can write our product rule as this as well. We can have p of xy equal to the conditional probability of x occurring given that y has occurred, multiplied by the probability, the marginal probability of y occurring. So that's really neat. That shows how we can manipulate our joint probability to be like this factorization of two different terms. So in machine learning and in Bayesian statistics, we are often interested in making inferences about unobserved or latent random variables, given that we have observed some other random variables. So we want to know what is happening to x given that we already know what's happened to y. So this is where Bayes' theorem comes in. So if you think about machine learning in general, we need to collect tons of data and we train our models on that data to find patterns. And once we have these patterns, we can use them to make predictions on new data. So in a nutshell, that's essentially what Bayes' theorem is trying to do. So let's go ahead and derive Bayes' theorem. So over here, we have two different equations. Let's call this equation 1 over here and this equation 2 over here. We can see that both of these equations equal the joint distribution of x and y. So following what we know about substitution and elimination and solving linear systems, we can equate these two equations together, and then we can rearrange for the probability of x given that y has occurred. So say we already know about y, but we want to know what's happening with x given that we know what's happened with y. So let's equate those two equations. So this gives us p of x given y multiplied by py equals to p of y given x multiplied by p of x. So we're simply going to divide both sides by p of y, and we'll see what we get. So as a result, we now have that the conditional probability of p occurring given y has already occurred equals to the conditional probability of y given x has occurred multiplied by the marginal probability of x all divided by the marginal probability of y. And hey, guess what? This here is Bayes' theorem. So we just derived that by understanding what joint probability is and our understanding of the product rule and how it relates conditional probability and marginal probability. So that's amazing. So now let's take a second and actually observe every point of this equation so we can have a deeper understanding of what Bayes' theorem is. So this part over here at the front, this is called the posterior. This over here is called the evidence. This part here is called the prior. And this part over here is called the likelihood. And now let's take a second to understand what each of these means. So starting with the prior. So p of x is a prior. So this encapsulates our subjective prior knowledge of the unobserved or latent variable x before observing any data. We can choose any prior that makes sense to us, but it's critical to ensure that the prior has a non-zero PDF or PMF on all plausible x, even if they are rare. Okay? Now what about the likelihood? Let's take a peek at that. So the likelihood is the conditional probability of y given x. It describes how x and y are related. So in the case of discrete probability distributions, it is the probability that the data y, if we were to know about the latent variable x. Okay, so what is the probability of y if we already know about x? Note that the likelihood is not a distribution of x, but only in y. And now let's look at the posterior over here. This is our value of interest. It is the main quantity of interest in Bayesian statistics, okay? Because it expresses exactly what we're interested in. So we want to know about x after having observed y. So it's helping us gain that new information that y is unlocking for us. Lastly, let's take a look at our evidence. So our evidence is independent of x. So that means that it ensures that the posterior over here is normalized. So it's always good to have normalized equations so that we have more reliable result. So finally, looking at Bayes' theorem, why is it important? So Bayes' theorem allows us to invert the relationship between x and y. So it's also known as a probabilistic inverse. So that is really neat because we can see how we can easily rearrange this equation so that the posterior might be the conditional probability of y given x instead of the probability of x given y. So in Bayesian statistics, the posterior distribution is a quantity of interest as it encapsulates all the available information from the prior and the data. So that's why we really want to know all about Bayes' theorem. So in today's lesson, I taught you how to derive Bayes' theorem, and more than that, we learned how to dissect Bayes' theorem. We understand what each term means, and we also learned about its invertibility property so that we can, if we're given data in a different point of view, we can invert our equation, change it around so that we can make new conclusions based off of what we know. And it's also a great tool, like I said, for machine learning, as it has that fundamental property of we're trying to take what we know, learn from our previous patterns to make future predictions about new data. So if you enjoyed this video, please drop a like and subscribe for more math videos. Drop any comments that you have below if you have any questions, and I look forward to seeing you next time.